Evening, folks. Thanks for having us this evening. My name's Marcus, and this here's Hong. We work for Mellori Solutions. We're a defence contractor based out at RAF Edinburgh, and we maintain a bunch of fancy radio systems on behalf of Defence. We'll talk you through one of our little systems over there afterwards, but to begin with, we'll give you some basics on radios, RF, EW spectrum, and hopefully bring you along for a little bit of a journey.
Yeah. Pretty much. Yeah, so hopefully you get a bit out of this. Any questions you've got as we go through the presentation, please raise your hand. If you've got any concerns, some stuff that you don't understand, hopefully we can give you some sort of a different analogy to what you may think it is, and hopefully it'll help you out with understanding pretty much what electronic warfare is, what we do at the RAF base, at the civilian level, and we'll try to explain a bit more that way for you guys. Yeah, beautiful. So, our learning objectives for today is give you some sort of wireless principles and applications that you can see and how that ties into electronic warfare. We'll talk about the electromagnetic spectrum. Is everyone happy with the electromagnetic spectrum and stuff like that at all? Yeah, cool. Talk to you about what EW fundamentals is, give you a basic breakdown of antenna theory, what sort of scans and tracking they might use in the environment to detect a target or to better assess the environment, to grab those targets that it needs to grab. And last but not least, Marcus will explain the EW tree pillars and the integration of how these systems are combined to form a closed loop system for self-protection, enemy attacks, etc., and protecting the assets, as well as, most importantly, the personnel on board of those assets. Yeah. All right. Is everyone happy with what that wave on the very right-hand side is? Everyone ever seen a wave like that? Those that do a lot of RF, yes, you definitely have seen that. So that's what we call an electromagnetic wave. Cool. So the red portion of the sine wave is the electric, in this particular case, we'll say that, and the blue portion is magnetic. So these waves are obviously introduced when you start running some sort of fast current into a medium. In that case, most of the time is electrical wires or coaxial cables, and it will create this EM wave. So then the purpose of, I guess, radiation or wireless principle is that we radiate this into the atmosphere, and with that it contains information that we can utilize. So, and they travel at the speed of light, so it's quite quick. Again, these waves, or all wireless principles and applications, are based on these waves. Out of these waves, there's parameters that can be grabbed to actually get some information out of it. So, next slide. All right, so when we break down these waves, let's break down just one portion of it. Let's just say this is the electric field. In that case, these waves have a certain amount of frequency, always a frequency, and it's represented by the cycles, or complete cycles, against time. So we have what's called a power ratio against a time ratio. For every cycle, sorry guys, so come back a bit, Marcus. Go back. Yeah. So every complete cycle against time, every second, every complete cycle is 1 hertz. So for example, if we talk about, say, SAFM, we operate at 107.1 megahertz. So in that case, just imagine that there's about 107.1 million cycles of these per second that's coming out to get that frequency for a radio station, in that case SAFM. Happy with that? So that's one part of the parameters this wave we can actually measure. Next one. The next is wavelength, which is the measurements of the peaks to peaks of these particular waves. Usually this is measured in meters, and from an RF perspective of radar or comms and radios, we use frequency. But when we start talking about wavelengths, we utilize that in lasers, etc., and the measurements of lasers, because for calculation purposes, it's a lot easier. Next. And then we need some sort of power. So those portion there gives you how much power is within this wave. So the larger the amplifiers or the transmitters, the more power you're going to have. Obviously, vice versa with the lower power transmitter, etc. Last but not least, we call what's called polarization. So when we transmit these waves and receive these waves, if the polarizations don't match, we won't get any signals. So ideally, we want to match that polarization from the transmit in to the receive end to be able to get that signal and detect a certain signal as well. And it travels at the speed of light, pretty much like this. So, in what we talked about these waves, there is what's called an EM spectrum, which is the range of all these waves or these applications sits in and operates in. So as you can see, we've got to the very left side, extremely low frequency from the 0 Hertz range, all the way up to the petahertz range in your gamma rays, that's outer space. So where you would see a lot of stuff that you operate at is pretty much in these range here. So where your radios, etc., that you operate, SAFM, etc., are in the megahertz range. As we climb up to the gigahertz range, that's where radar will sit, and even higher, we go into infrared and ultraviolet applications, etc. Cool. So that range is so big that every application we know right now that's to do with wireless will sit within this spectrum. Happy with that? Cool. So why is this important? Very clever individuals, heaps clever than Marcus and myself, have developed these principles and utilise it in applications that you see today. So your keyless entry into your car, your garage, your doors, etc. right now is based all upon these principles. Yep, from your Bluetooth and your Wi-Fi that you can use your internet with, your TVs that you see, even these projectors, are all based on these waves and these applications and the principles of wireless communications. Then you've got microwaves, thermal detections, and predominantly in radar aspect, UV and IR is a lot to do with military applications. And obviously the list goes on. And those are just some examples of what wireless communication is all about. And it's the basic of these EM waves and the applications for EM waves. Cool. Marcus?
All right, so for a bit of an intro to the electronic warfare now that we've spoken about radio waves and EM spectrum, I'm going to sort of give you a rundown on what electronic warfare is. Essentially, it can be defined as a process or an action taken to gain advantage in an operational environment. So that may be to gain better situational awareness of what is going on around you. It could be to interrupt an opponent so that they can't cause you harm. And it could also be used as an attack vector instead of a kinetic weapon. There's basically 3 pillars to electronic warfare. So electronic attack is using something to actively jam or deny someone access to that spectrum. So you could be disabling their communications, you could be stopping their radar systems working. Everything, as Hon alluded to before, is done wirelessly these days. So that's sort of our electronic attack side of things. ES, or electronic support, is gaining an awareness of what's around you. So we can look around us and see what's physically there, but electronic support is that what radio signals are out there, what's over the horizon that we can't see and we can't detect any other way, but we can see the radio signals that are coming from them. And then electronic protection is used in conjunction with that ES, so the electronic support, to protect ourselves from an opponent. And we can do a couple of things. We can mask our signatures. We can release chaff into the atmosphere so that it clutters our signals so that people can't see us. And essentially that's used to protect ourselves. Now, the basic electronic warfare methodology is avoid detection. If you can't be seen, you can't be found. Avoid tracking. So even if someone can find you from your radio signature, then we want to avoid them being able to track us. And that's things like reducing our signature or throwing noise into the atmosphere. We like to identify and record what we see out there in the environment. So it's nice to know who we're going up against, and it means that next time you see somebody's signature, just like when you see a photo of them, you can recognise them and say, hey, we've seen this fella before, and now we know what he's up to. If everything fails and we are under attack, then we sort of start going into this implementing countermeasures and manoeuvring, and that's where we fire off chaff, which are little bits of tin foil that float through the air. We fire off flares, which are a hot little burning flare that presents a more attractive target to a weapon that's inbound to basically cause you harm. And then we want to vacate the area and get away as quick as we can. And obviously the final goal of EW is don't get killed when you're in a hostile engagement. There's lots of EW relevant threats out there in the real world. So we've got radar-guided missiles, we've got infrared-guided missiles, and they will primarily target the hot exhaust plume that comes out of an aircraft, for example. There's radar-guided guns, like CWIS, up on the right-hand side there. Anti-radiation missiles, which will seek out noisy radio targets, and you make yourself a homing beacon by having a big loud radar transmitting or some other form of radio. And then there's the SPY-6 radar. I mean, there's lots of shipborne radars, and as they become more advanced these days, they make it easier to target people. And all of these work in conjunction, or these detectors work in conjunction with various types of missile sites, be they shoulder-launched rockets or shipborne torpedoes, or SAM sites, which are surface-to-air missiles that will target aircraft. There is various types of EW attacks, so going away from the threats that are out there, but to the attacks so that we can force projection, essentially, project ourselves upon an opponent. We can use RF decoys, and these are little, the top left-hand side looks a little bit like a bomb that would drop from a plane, but instead of having something kinetic in it like gunpowder, it's just making a whole bunch of RF noise, and that will distract enemies that are out there. We have jamming pods, like it's slung underneath the Hornet there, and that makes a whole lot of noise, or it can go out and basically reach out and interfere with an opponent's radio systems. We have towed decoys on the right, very similar to the left RF decoy, but it's just towed behind an aircraft, and it will take your aircraft signal but put it 500 metres, a kilometre behind you, so it sort of confuses somebody else. Chaff, we were discussing, chaff is just little bits of chopped up foil. That's all it is. But those, as Hong was talking about wavelengths earlier, those bits of foil are cut to a particular size to stimulate a particular wavelength and to basically counter any threat. And then there's shipborne decoys as well, which can float out in the water or can be launched off the side of a ship. And they sort of work the same as the RF decoys and towed decoys, where they present a more attractive target to an opponent. There is various things that we use to indicate that there's a threat in the environment. There's different systems. So we have radar warning receivers, like on the Apache there. Essentially what that's doing is, it's like the radar detector people would have in their car. It's looking for radar emitters that are out there in the real world, and if it sees a hostile one, it lets you know about it. Laser warning receivers we mainly see fitted to land-based vehicles. And essentially, it's like if the police were pointing their laser speed camera at you, those receivers would say, hey, somebody's targeting you with a laser. And nothing good ever comes of that in a defence situation. We have ESM systems, electronic support measures, and that essentially paints a big, pretty picture of the RF world around you. So obviously we can't see those waveforms, and that will make them visible. And we'll demonstrate that on some of our equipment over there afterwards. There is civilian equivalents of a lot of this stuff. I mean, we're coming to you from a defence sort of perspective, but in the civilian world, there's lots of people like yourselves who like to tinker and play with gadgets, and there is civilian stuff that isn't the big fancy shiny defence assets. Hack 1 RF here is a fancy software-defined radio. It's about $600. It goes up to 6 gigahertz, and that essentially lets you create all of these decoys that we were talking about. That there can pretty much pretend to be any radio that's out there. The flip is 0 in the middle, and we've got one over on the table to show you afterwards, is a little handheld, pocket-sized recorder and transmitter. So that thing there can take the radio transmissions from your car alarm remote, from your swipe card or something like that, and it can copy them and duplicate them. IR blaster on the right. It's just a really big, fancy remote control, infrared remote control for your TV, but it's super powerful, and we can suck in infrared signals and then we can replicate them again. And there's a couple of different options out there. This stuff here is the civilian equivalent of what we do in defence, and it's out there in the world. And it's becoming quite relevant these days with, unfortunately, break and enters on cars, with the new proximity keys, where you don't have to actually push the button on your key. Essentially, criminals can put one box near the car and have a second person over near your house and walk around until they get in the proximity of your key. Not to scare you, but don't leave your keys sitting on the hall stand at the front door. Essentially, put them a bit further back. So anyway, we'll hand back to Hong for some radar theory.
Yep.
Got that one.
Can I ask, can you pick up on anybody else's, like you're talking about defence and what you set up, can you pick up on anyone else's signals so that even though you're blocking it, can you find out what their signal is?
Yeah.
Okay.
We'll show you in a sec with that as well. See the difference. Alright, so Mark has given you the hierarchies of, all the EW components that we have in defence and so on.
And not to scare you.
I'll give you some basic radar theory to how these all applies in to how those higher components actually works now.
So,
It should be good that way. Alright, so.
technology problems.
Just give me a shout out if you know how radar works.
Yeah, I do.
Yeah? We're happy with that? You know? Cool. So, radar works simply by just radiating those EM waves that we talked about before at a certain frequency, and it radiates into the atmosphere. So, that's all it does, the transmitter, it radiates, and it's hoping to get some sort of reflected echoes. Cool? If it doesn't get any reflected echoes, it doesn't know anyone's in that atmosphere, anyone's in that environment. So it needs a reflective echo to go, okay, well, I've received something back, I know that there's someone there, what can I do with that now? So that's what we talked about, the parameters before, the frequencies, the polarization, they all make a case to how these signals come back to you as a radar system. It awaits for returns, and then it gets a reflected wave, then it can process a signal to tell the operator that, okay, something's in the atmosphere. Right, but then it's also affected by things that are in the atmosphere, whether that's cloud, rain, hail, mountains, terrains, buildings, etc. What it's going to do is when you transmit a signal, you're hoping for that reflected echo, right? So that will give you the target indication or whereabouts it may be, etc. There's more processing to do, but that's the basis of it. But it also can scatter, and that also ruins your chances of getting that signal back. Cool. And you get absorbed by rain as well, and hail, etc., haze, and that also will ruin your signal or the ability of detecting a target. So this all comes into play. Yes, you have these systems that detect stuff, but if the atmosphere stops you from detecting those systems as well, it makes it harder. Cool. So interference by EM radiation can include absorption, attenuation through the atmosphere, reflections, obviously is that what we need, scattering. If you go and transmit through something like glass or water, you're going to have some sort of bending that's going to occur as well, and we call that refraction. And then as you fly past the radar horizon, that also affects the way the radar is bounced back to the, from the target as well. Ultimately, they all affect the way you process those signals. And you're either going to have something that's going to make the signal stronger or decrease the signal, and we call that destructive and constructive interference. Everyone's happy with that? So that's the baseline. Okay, so we talked about how we get the reflecting echoes. We've got two basic radar systems that does the job. One we call pulse radar, which relies on only one antenna, which we will transmit the pulse, awaits for that return, and then processes that information. So we call that a pulse radar. We've got the other sort of radar system that's called a continuous wave radar. It needs two antennae. One of the antennas purely to radiate that signal, and the other is to purely receive. They both do the same similar jobs, but they have different purpose. You'll have the pulse radar generally on smaller platforms, air platforms, etc., where less power is available and less weight. Something like a continuous wave, you're going to use that down on the ground a lot more, like your ground radar station and so on. Happy with that? So how does a radar determine a bunch of these information? So basically from a basic level, to determine presence, we all know that we need that reflective echo. When there's a reflective echo, the radar assumes that there is someone out in the environment. Cool. And to determine range, what it does is it measures the time it takes to hit that reflective echo and then receives that signal. And then it just doubles that time and calculates that, yes, I've got a range now. Happy with that? Position, so obviously when it scans and it detects a signal, it will assume that, yes, that's the position that you're at. Are we happy with that? Enclosing speed. Everyone heard of Doppler? Yeah, so it uses that principle. So if someone is travelling away from you, the frequency is going to be a lot less compared to someone that's coming at you. The frequency is going to be a lot higher and faster. Just basic. And then we've got the last but not least, the identity is through what's called IFF, or Identified Friend or Foe, which needs a sort of responding system to know that it's a friend or foe. Happy with that? So that's the basics of how radar pretty much identifies the target, determines range, position, and if it's a friend or foe. Obviously it's a lot deeper than this, but we'll give you a basic level. Alright. Have you ever seen this before? So this is just...
So there's something I want to talk to you about before we go to the park. I don't care if anybody gets it. I'm going as the Doppler effect. No, that's not. If I have to, I can demonstrate. Meow. Terrific. Hi. Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train? I still don't get it.
I'm the Doppler effect.
If that is some sort of learning disability, it's very insensitive.
Why don't you just tell people you're a zebra? Why don't you just tell people you're one of the seven dwarfs? Yes, well, I'm the Doppler effect.
Everyone happy? Alright, so before we've had that information where you've got that sine wave and we break down the different parameters, radar likes to operate not in that time domain, but in what we call a frequency domain. So through fast Fourier transform, we just convert that same signal from this time domain with the sine waves into what we call a frequency domain, and we start getting these little clips that are shown. Radar likes to have this because it's easier for them to process and decipher some information. And then we can further break it down for you guys how this information is processed. So just like your finger or thumbprint, we call that our radar signature. Every radar also operates at a certain frequency, a certain pulse repetition with a certain pulse width. So your fingerprint separates you from everyone, so does a radar system's fingerprint. So the three form parameters are what we call basic identifier features of a particular radar system. So first of all, you need that frequency we talked about. So how many cycles per minute it gets converted to frequency, so we know the frequency. From there, we can measure what's called a pulse repetition interval. So we have what's an on time and off time. So predominantly this is a pulse radar. During its on time, you'll see a pulse, like a number 1 or 0, and the off time is off. So it will stay on. If any signal is reflected back during its on phase, it doesn't know, it doesn't care, because it's getting clips and it doesn't know that's there. It waits till it's off time and then it starts listening to that. So if a signal is detected on its off phase, it will be able to process that signal. Are we happy with that? And then last but not least, the pulse width will dictate it on and off time, and that ever changes depending on the modes. Oops. Every radar system and every mode will have a certain frequency, a certain PRI, and a certain pulse width. Just like your fingernails or your fingers, they have grooves and crevices. That's how we determine which type of radar is either a friend or foe, or it's attacking us, or what is its plan to do with the modes that it's in. Are we happy with that? So three identifiable features. They are the radar frequency, the pulse repetition interval, and the pulse width. Cool, so we already know that radar frequencies, and we talked about those sine waves. Radar generally operates between your 5 and 20 gigs, and 26 gigahertz up to the 40 gigahertz range. The reason that the 20 to 26 is non-existent is because the atmospheric attenuation between those frequencies is extremely high. So you try to transmit in those particular frequencies, most of the time you're going to get a high attenuation, so you lose a lot of power. So it damages your return echoes. Are you happy with that? We'll show you that as well. Yeah. This is how radar detects targets in a positional aspect and also a distance aspect or range aspect. So depending what beam, so not all antennas are made the same. Some antennas are radiating 360 degrees, some are directional, which is what most radar application is all about, being directional. And then depending on how the radar antenna is designed, it affects how portion that beam width it looks at. So if, let's, for instance, say for example, we have 4 aircraft in a positional aspect or varying aspect. if you have a larger beam width and you hit two of these aircraft within your reflected echo, your processing is going to assume there's only one target and not two targets. Cool? So in order to discriminate the angular position, we need to decrease that beam width to be able to see those targets from an individual basis. So again, this is positional or bearing, so you're only getting the angular position or bearing of that particular target. You still don't know the range. So we talked about previously PRI, the pulse repetition interval then affects the range by how it sees those particular aircraft or assets in the air from a distance perspective. So if you have a larger PRI, in this case, it's going to also assume that those two aircraft are at the same distance, or roughly about the same. So to separate that, we have to either make our PRI smaller to individually see separate aircrafts. So from an angular aspect, the beam width affects how the radar sees the target, and from a distance aspect, the range, or PRI, affects the range. Are we happy with that? So that's how the radar sees the world. Like we visually can see 360, right? We just have to turn. But radar is just blotches. You can't see everything. So it sees blotches, but it has to use certain things to be able to see the overall aspect of the environment. So then we come down to what's called a radar resolution cell. So the radar resolution cell is a mix of that range resolution and angular resolution, both in the azimuth and elevation phase. So the radar resolution cell is the smallest volume that this radar can see in the environment. And it's up to design. It's not up to what you can do, it's just design of the radar. This is the smallest you can see, and that's what you've got to work with. Are we happy with that? So that's affected by the range and the angular resolution. What also plays a key effect of how radar detects the target is what's called a radar cross-section. So it's pretty much how the object looks to the radar system. The smaller the RCS, the less observant that object is to the radar system. So if you want to compare a bird and ourselves to a radar system, we're going to be shown as a large object. Are we happy with that? So in a military sense, what changes this affects is the shape, the position of where you stand and how that radar works, the materials, the reflectivity, obviously polarization is key as well, and frequency and wavelength that you use during your transmission phase. So a great example is I've got an RCS of the F117, F35 and F22. They're what we call stealth aircraft, but they still all have different RCS characteristics. So if you look at the F117, the RCS is a little bit smaller than the F35 and F22. So the term stealth is not invisibility or anything like that, it's how you look to the radar system. And how small you are to that radar system. Is it able to detect you? The smaller you are, the less chances of them deciphering your information or detect you as a target. Are we happy with that? And then we also have what's called minimum maximum detection range of what the limits of that range that the radar can actually transmit to and be able to detect targets. And it's based on that radar range equations. Just to give you an example. Happy with that? Cool. So we've just thought about the basics of how radar can see and individualize a certain target and object. So we talked about range resolution and bearing resolution. Again, we're only seeing blotches now. Now we have to go, how do we utilize that blotch to cover the whole environment and what we need to do with that radar? You happy with that? So first of all, obviously we're going to need an antenna to radiate the signal. And that's the purpose of an antenna, to radiate these RF signals out. I'm not going to really go further than that. But advanced antennas will have different designs and different applications. We talked about polarization. It really plays a key effect. So if you're transmitting on something that's a vertical polarization where the signal's like this, but you're receiving on a horizontal signal polarization where the signal's in a horizontal direction, you're not going to get any signal back. You literally have overall infinite loss. So hence, this is a quick way to mask yourself against a target. If you know that they're transmitting on something that is vertical polarized, you can just send back signals of a horizontal polarized and they won't be able to see it. That's a quick way. And it just shows you that the examples of vertical to horizontal to how much power is lost. As you see, if you're vertical and horizontal, you're infinite loss. Theoretically, but atmosphere plays a key effect as well. You guys happy with that? Not going to go in order. Has everyone heard bandwidth before? Happy? Yeah. So bandwidth is a range of frequency where your radar system or your antenna is capable of operating. So obviously you've got the center frequency where the best signal is. So for example, 107.1, you tune to 107.1, you're going to get a perfect signal from that particular station. Depending the distance you are to obviously the transmitting station, right? But if you go and select 107.0 or 107.2, you're going to have half the power. It means that half the loss of that signal is gone. So you can start hearing those noisy background signatures going on into that signal. We happy with that? And that's the half power level. Obviously, anything outside of 107.0 and 107.2, guess what? You've lost that signal. And that's what bandwidth is all about. Having that range that you can listen to the signal or the radar capable of transmitting on that range. Happy? And then how that turns into a main lobe and side lobe. So radar again, radar we transmit with the main lobe. How big that bandwidth is obviously determines how much power the main lobe and the range it reaches. And then it's also undoubtedly all radar systems will have a side lobes. Don't care how big the radar system is, it will have some sort of side lobes. Cool. So that's loss of power. And again, any signal that you receive from here inwards is only going to be half the power. So that depends on how good the receiver is to be able to process that signal and identify that target. But most of the time when you get signals in the main beam, you're going to get a good detection back. So your chances of identifying and processing that target, it's high, it's very likely. I'll talk to you about different type of antennas. We've got dipole antennas. Everyone's seen dipole antennas? It's just pretty much, it's built on a quarter wavelength, half wavelength, etc. what you want to do. But that's one of them.
That's a dipole, so it's just a little straight stick, essentially.
Cool. So if you have your coat hangers, the metal coat hangers, you bend them to a right portion and split distance. You also make a dipole antenna as well, to a certain extent. The pattern might not be like this, but offsets a little bit depending how you bend it, etc. So that's one way to make one.
I've messed with Hong's slide
Perfect.
pack here. Do you want to explain this one or do you want me to? So, talking of a dipole antenna, essentially, straight antenna up in the air, different gain patterns, and it's relevant when you put an antenna on your car for UHF radio, will have different emission patterns. So, if we use a 3 dB antenna, it's a low gain antenna, but you actually get a really nice big donut around your car, and you can pick up people near you really well. If you put a 6 dB antenna or a 9 dB, that pattern gets a lot tighter and a lot narrower, so looking down from on top or beside the car, you get lots of distance and lots of throw with your UHF radio, but what you'll find is if you're pointing up a little bit of a hill, the people underneath you may be outside of that reception area.
And then you have a parabolic or what we call directional antenna. So your TV antennas that you have mounted up, the Yagi ones, they're all directional. So sometimes when you get pretty bad reception, could be the atmosphere playing with it. So you point it a little slightly offset to get a better reception, etc. That's what directional antenna is all about. It directs at a certain direction for the transmission and receiving process. That plays a key effect, I guess, on how you radiate that signal out. Modified parabolic or slotted waveguide, you get what's called a fan beam. So instead of the signal being like a sharp sort of beamwidth type, you open that signal up into a fan beam type. So you're covering more area now. Remember how that radar can only look at blotches? Now you've enhanced that blotch into that vertical, or the vertical elevation segment of the area you're looking at. And you'll see that on sheets as well with nav or sort of waveguide antennas. Then we go into a more advanced antenna type. We call this the planar or phase array. So this uses the principle of beam forming. So this beamforming techniques will allow the antenna to get any pattern of desire, from a pencil beam or your beam width that you saw before to a more open fan beam, etc. So depending on what mode that the actual system is selecting at the time, it changes that beamforming ratio to either type directional beam type or an open fan beam transmission. And that's what beamforming is about. So it relies on the phase shift. This antenna will go first, and as constructive interference occurs, it starts shaping the actual beam to a certain direction to a tighter beam width if you want it to as well. Everyone happy with that? Again, in the more advanced aircraft, 90s, 2000s, etc., you'll find. And then you have those brand new specky antennas. We call that active electronic scan array antennas. So you'll have an antenna base, and you have modular within each of those antennas, and each of those modules are actually an antenna receiver itself. So they work individualized as an antenna and a receiver. So on a massive scale, you can have 1,000 of these modules on that antenna. So literally you have 1,000 antennas. And they all can pinpoint and transmit at different times, and all at one time as well. You find this in the more advanced military platforms. Right? So your stealth jet fighters, etc. you see nowadays, those are what you're going to find. Happy with that? So we talked how an antenna affects how it looks into environment, because radar looks in watch, and the patterns of that beam is how it looks. And the antenna you use to give you a bigger look area, or viewing area. Now you've got to rely on some sort of scan to now cater for the azimuth or the 360 environment. So radar scan help radar systems search for targets of interest in the open environment. Once the target is obviously detected, generally you'll have something trying to track you to find out more information about you and investigate the target's intent, and information such as varying range, velocity, etc. we talked about can be accomplished there. Furthermore to that, once you track, and a missile is tracking area, in the final aspect of that phase, it will lock it in. And that's how it starts to track onto the target. And obviously until it hits you, that's the final end game of the missile. Cool? So search, track, and lock. So you'll see this commonly in a lot of military movies. You'll see a blip, and then you have that circle, and then you get the target of interest being appeared on the blip. Pretty much that's what a search scan is. It just scans horizontal 360 degrees with that watch of your beam width, and it scans around. Happy with that? See that often? And then you have what's called a sector scan. Instead of doing a whole 360 azimuth environment, you blotch in little sectors. Right? Could be 90 degrees, could be 20 degrees. That's all controlled by software and the user as well. Or you've got a different scan pattern where the antenna will be pointing forward, but it rotates outwards. So it looks in that direction, but then it's covering more of an elevation as it rotates out. Cool? And this is how radar looks at the environment now. You're starting to cover more area, more of the environment, look at more objects of interest. And then you have helical, so it will scan 360, but for every complete rotation, it raises its elevation. Now it's covering elevation and azimuth as well. Cool? Software control. And then some more advanced stuff, it can go across, down, back the direction, back down, and across. So now, again, it's covering elevation, but also a certain sectional area within that environment. Happy? And then you've got the most advanced radar system. It looks at 360 every direction, tracks everything that it can see. If you fall within that space and you don't have any protection, it will track you. Cool. And that's your AES antenna. Happy with that? We'll give you more examples. So obviously now you use the scan, alright, to scan for your targets, get the environment. Obviously once you find target of interest, alright, I'll I really want to start looking at you more and find out more information about you. Why are you in this environment? Why are you in my airspace, etc. And that's what ATC, air traffic control will do once they find it and start looking at more information. In this, our case, militarist perspective, we want to track what's out there. We want to know why this aircraft's coming in or this platform's where it is. So how does it do that? The first part of it is what's called load switching. What it does is it transmits, now that you know that it's there, you transmit a beam up and a beam down. If you don't get any return pulses, you know that that's going to be centered. But if you get a return pulse as you're beaming up, that means that it's sitting up high. So what the user tends to do is drive that radar antenna up a little bit to center the target so that you're not getting any reflection back. Are we happy with that? So this is what happens. You get a pulse, and then you get another pulse, return, and if it's two identical pulses, you can say that that's pretty much centered, dead centered. If something is high pulse, when it goes up high, you have to shift it back up, and that's over time. Are we happy with that? So that's the most basic tracking method. This is 1960 stuff, 1940, 1950, 60 stuff. Then we got what's called conical tracking scan. So you fire a lot of pulses at a certain degree or a certain looping angle or squint angle, and then as you can see, it flies around. When it hits the 270 degrees, it gets a massive pulse. So the system then automatically drive it to the left until that all the pulses are about centered like that. That's conical tracking. Are we happy? And monopulse, instead of the one up and one down, you get 4 pulses at one. Can be 8, can be 16, depending on the systems. And then you're looking for those returns, and then that's how you know it's centered. If any of that one of these pulse is offset compared to the other, the system will automatically drive to center the pulse again. And it's constantly looking, constantly tracking. And then we've got track while scan where it will hit the target. Remember where the target is last. When it hits the target again, it will compress that signal and process it, and then it will know how the target's moving. And it keeps track of that target. And then your advanced radar gives you full situational awareness of the environment. Regardless of what you want to do, it's going to see you, it's going to process you, etc. Which is called search while track. You can do multiple targets at any one time and track multiple targets and then search at the same time as well. We have it.
On a global scale, vessels and marine personnel carry out missions at sea. Thales introduces a new application based on a proven IAA technology. The Thales IAA dual-axis multi-beam concept.
Because it's a slow-moving asset, you want to have the best detection system, right?
The IAA technology uses simultaneous multiple beams in azimuth as well as in elevation. This enables the combination of fast reaction and long observation time. A variety of marine fleets equipped with Thales radar systems using this technology can now identify a wide spectrum of targets in a matter of seconds. The NS-100 radar scans the full area of air and surface targets. It automatically detects all targets, ranging from small, slow UAVs up to high cruise missiles in one mode. The active missile support assists in high-threat scenarios. Situational awareness with extended weapon support in a single mode. The unlimited update rate helps to defeat the most challenging threats. with the ability to detect targets at extreme distances. Its excellent features make it possible to detect stealth threats and ballistic missiles from launch up to impact.
Pretty much just showing you all different type of radar working together so you see the overall 3D picture of the environment from a radar aspect.
Wait, you don't have a mouse that works in mid-air?
If you click on the link, it freaks it out. There we go.
I'll pass over to Marcus.
Ooh, lovely, thanks. That's right, buddy. Oops, hang on, go back a page there, give me a second. So we've explained to you basically how antennas work, what the EM spectrum is and how signals make their way through the air, how we detect signals and identify signals, so their fingerprint, so based on their frequency, their pulse width, their PRI. We've gone through different types of scan patterns that radars use, and now it's sort of how all of that stuff comes together and we actually use it in the real world. So essentially our purpose is to identify what's out there, either an unknown target, a friend or a threat. Each of those have their fingerprints. We use our radar systems to identify them. We use our receivers to identify them by looking at the specifics of their emitters. Once we have received those signals, we go through and we analyse and we decipher, and we keep good records of most emitters that are out there in the world, and we have tools and systems where it allows us to basically look at a signal and either manually with a skilled operator or automatically through software identify it and label it. Once we know what that threat is and we've put it into our system, we can figure out how to counter it. And so we'll display it for the crew so that they know what they're dealing with, and then at the same time we determine what is the best way to counter that threat. And that may be to use active jamming, it may be to dispense flares or chaff, or it might be to deploy a countermeasure against it, so a kinetic threat. Right. Yeah, I'll skip that. So the EW spectrum is a busy place. In a battle space, just in this room, and we'll show you shortly when we turn the spec hand on there is radio signals absolutely everywhere around us. There's command and control links, so from people on the ground talking to each other with radios, with vehicles talking to each other and controlling each other. We have data links up and down to satellites, we have electro-optical sensors, so we have cameras, we have infrared sensors, laser warning receivers. This is a very simplified battle space, and you can see how much is going on. But you think once you start putting 20, 30, 40 interconnected individuals on the ground who all have radios to each other and little smart tablets on their wrists so that they can get satellite feeds and aircraft feeds, becomes an extremely complicated space. And this is sort of where we play in, and the equipment we have aims to emulate all of these signals. So we can present a realistic environment, RF environment, for defence to operate against in training. That's it for the presentation.